Hey guys, Miss Marusik here, and in this video we're going to look at an introduction to gas laws. Now, before we get into the laws themselves, we're first going to talk about the kinetic molecular theory of gases, which is basically a set of postulates or points that summarize the behaviors that gases typically demonstrate. And not all of these are going to be new to you. A lot of these postulates you are already familiar with from when we compared solids, liquids, and gases back in the fall semester. But this is a kind of set guidelines illustrating how gases should be behaving under ideal conditions. So our first point here says that gases consist of molecules whose separation is much larger than the size of the molecules themselves. Now, what that means is that if I could look at the radius of a molecule of gas, that I would see it's very small in comparison to the distance between that molecule and another gas molecule. So again, the separation here is larger than the size of the molecule itself. And to be honest, this picture doesn't even do it justice. Like, the separation is way bigger than the size of the molecule. This is, again, not even to scale. So to kind of summarize this point, gases are mostly empty space, which is something that you're already familiar with. If I compare a gas to, say, a solid or a liquid, those molecules are much more condensed together than we see with a gas. Another behavior is that particles in a gas move in straight line paths in random directions. What that means is that if I could follow the pathway of this molecule of gas, I would see that it moves in a straight line path until, say, it either bumps into the wall of the container or bumps into, say, another gas particle. And when it bumps into something, it'll basically bounce off and go at an angle in another straight line path in random direction until it bumps into something else, and then again it'll go in a straight line path in random direction, and it'll just keep on moving around the container like that endlessly, basically. Now, there's something else about those collisions that we have as we move in those straight line paths in random directions. You notice it says here that particles in a gas collide frequently with the sides of the container and less frequently with each other. Now, I'll be honest, that's just sheer probability. Like, if I think about this gas molecule, it's way more likely to hit into the side of the container than it is to hit into another very small, very tiny gas particle. It's, again, sheer probability there. But there's a few other things about those collisions. First off, if a collision does take place, it is an elastic collision. Now, I know those of y'all in physics are a little bit familiar with that term. For those of you that are not, what an elastic collision means is that overall no energy is lost or gained in that collision. It could be transferred. So say I have a gas molecule moving really fast and it bumps into one moving really slowly. That fast one could transfer some of its energy to the slower one, and they could both be moving at, say, a medium speed once they're done, but overall the total energy remain consistent in that collision. That overall, the sum of the energies before the collision is equal to the sum of the energy after the collision. Now, something else about collisions that I went ahead and put on here, even though it's technically not part of this postulate, is that as the number of collisions with the container increases, that is indicative of an increase in the pressure within that gas. And we're going to talk quite a bit about that as we get into some of our gas laws, so I thought I'd go ahead and put that relationship here. Now, the next one is another familiar one. Particles in a gas do not attract or repel one another as they do not sense any kind of intermolecular force. Remember, as a solid, we have those strong IMFs. As we get to a liquid, we've weakened them a bit, but as we get to a gas, those IMFs should be completely broken. So again, that one shouldn't be anything new to us. Now, the last one here talks about kinetic energy, and it says that the average kinetic energy of all the gas particles in a sample is proportional to the temperature. Basically, what that means is that as kinetic energy increases, because temperature is a measure of average kinetic energy, we should see an increase on our temperature scale as that kinetic energy goes up. Now, we have to be really careful. The proportionality is only true if our temperature is in Kelvin. Remember, Kelvin is that scale that has no negative numbers. So as, say, maybe the kinetic energy doubles, your temperature would double if you're measuring temperature in Kelvin. So you've got to be really careful there. You're going to see on all of these gas relationships that we're going to talk about in a few moments that we have to calculate them in Kelvin, or it doesn't work out. The ratios don't hold true if I try to use a scale like Celsius where I have negative values. So we're just going to have to be really careful with those temperature units. By the way, these are obviously kind of ideally how a gas would behave. However, in the real world, sometimes we see some IMFs start to reform in a gas, or maybe, there's other factors at play where the particles of a gas get pushed one way or another. So it's not totally random. So there's other factors that could come in when you're talking about real life. So something that we talk about in AP chemistry is when gases behave most ideally. And they behave most ideally when those IMFs are totally broken. So it's best to have very weak intermolecular forces. Things with, say, London dispersion forces tend to behave more ideally than, say, a gas that has dipole-dipole or hydrogen bonding in it. But also, keeping those IMFs broken happens when our pressure is low, when there's very few collisions. More collisions we get, the more interactions we get. And also when the temperature is high, if we have lots of energy, that helps to ensure that our IMFs are totally broken. So we definitely talk about that a whole lot more for those of y'all planning on taking AP chemistry. Now, to start kind of jumping into our gas laws here, the first one we're going to talk about is kind of a standalone gas law. You're going to see all the other ones that we're going to talk about today kind of connect with each other. Our first one is called Graham's law. And it's kind of interesting because unless you've taken physics, you probably have never thought about this relationship that we're going to talk about. As we know, temperature is a measure of average kinetic energy. So temperature usually tells us some information about the speed of our particles, right? As our temperature goes up, our speed tends to increase. However, we have to be careful if I'm comparing two different molecules that have different mass. And the reason why is that if I have the same temperature, that means that two gases would have very similar kinetic energy values. But for those of y'all that have taken physics, you probably know there's a formula of kinetic energy equals 1/2 mv squared, where m is mass, what we're used to, but this little v is not volume here, but rather velocity. And velocity is telling us information about the speed of that particle. And so what happens is that since kinetic energy is impacted by both of these things, in order to keep kinetic energy the same, if I have two things that are at the same temperature, having a different mass might mean it's moving at a different velocity. So we have to be really careful there. Now, to give you a real life example of this, let's say I'm trying to, run a mile or something. And in order for me to run a mile, I would utilize a certain amount of energy. I would burn a certain amount of calories to run that. But then let's say some little kid who weighs way less than me tries to run that same mile. To burn the same amount of calories as me, they're probably going to be moving a whole lot faster. Why? They have less weight to carry with them. Now, when we're talking about, say, the weight of a molecule, instead of thinking about how many pounds I weigh, we're going to be thinking about molar mass. Molar mass is an indication of how heavy a particular molecule is. So just like with me, if it's a heavier molecule, it might be using the same amount of energy to move slower that something else that's smaller is using to move really fast. Okay. Now, technically, there is a calculation that you can do with this. It involves square roots and all kinds of fun things. However, even in AP chemistry, we don't have to utilize that calculation. We just have to be able to kind of explain this qualitatively. So we don't actually have to calculate with it. So what I want us to understand is that if I have two molecules that are at the same temperature, meaning that they have roughly the same average kinetic energy. That the larger the molar mass is, the heavier that molecule is, it's going to be moving at a slower speed, even though they're at the same temperature, even though they're utilizing the same amount of kinetic energy to move. Okay, so again, an increase in molar mass means a decrease in velocity. And that's going to help with that KE equals 1/2 mv squared. If mass goes up, velocity goes down in order to keep that kinetic energy the same. So again, it all ties back to that equation, even though we're not specifically calculating with it. So to kind of see how these examples typically look, here's one where they kind of describe to us a situation and ask us a question about the speed. It says, in scuba diving, a trimix is often used in the gas tanks of the divers. The mix contains nitrogen gas, helium gas, and oxygen gas. If it is assumed that all three gases are at the same temperature inside of the tank, which is a pretty good assumption. If you have a tank, and it's, sitting in a certain set of conditions, the temperature should be consistent throughout. Which of the gases molecules are moving at the greatest speed inside of that container? So what I did here is I went ahead and wrote down my three gases. Now be careful with nitrogen and oxygen. Those are diatomic, so I made sure to include that. And I went and wrote down what the molar masses are here. So for N2, that was 28.02. Helium was 4 grams per mole, and then O2 would have been 32 grams per mole. So out of those, which one would be moving at the greatest speed? Well, hopefully we figured out, hey, it must be that helium. That would be the fastest because it's the lightest particle. As far as the slowest, that would be our oxygen here because it was the heaviest molecule. The nitrogen would be moving a little bit faster than the oxygen, but definitely not anywhere near as fast as the helium. Now, another kind of real life example that's kind of a fun one, if you've ever seen this in action before, is about inhaling different types of gases. Now, I don't recommend doing this, okay? But I know a lot of you know that if you inhale helium from a balloon, that your voice gets all squeaky and high, But there is another gas that if you've ever seen this done, I know they did it on the Big Bang Theory on one of the episodes, and there's different talk shows where they've done this. If you search on YouTube, you can probably find somebody inhaling sulfur hexafluoride. When people inhale that particular gas, their voice goes like this, like it goes really deep and it sounds like they're possessed or something crazy. And so we want to kind of figure out, well, why does it do that? Why does helium make our voice high and sulfur hexafluoride makes our voice so low? So I wrote down our two molecules, and hopefully here, even without actually calculating the molar mass, we would know that sulfur hexafluoride would be way heavier. This would have a much greater molar mass than the helium would, right? Well, if it has a greater molar mass, what does that mean about how fast it's moving? Well, hopefully we know now that would mean it's moving much slower. Oh, I guess I should have put speed here. There we go. A lower speed. Now, think about what that means when it's traveling past our vocal cords. When we are, talking, what's happening is that air is rushing past our vocal cords. And air has a particular molar mass. Now, obviously, it's kind of a combination of gases, nitrogen gas and oxygen gas and all of that. But as it's rushing past our vocal cords, it's moving at a particular speed. And that causes a certain frequency of the vibrations that are occurring in our vocal cords. Well, here, sulfur hexafluoride is a much greater molar mass than any of the gases that are in the solution of air. And so therefore, it's going to be moving at a much slower speed. And what that's going to do is it's really going to slow down the vibrations on our vocal cords. They're going to be moving much slower, much less frequent, and that changes the tone of our voice. Whereas with helium, I'm not going to write all this out, but it would have a lighter molar mass, and so therefore it would be moving much faster, and so it's going to have a much more frequent vibrations. It's going to have much faster vibrations on our vocal cords, and that's why the pitch of our voice gets really high when we inhale that type of gas. So as crazy as this is, we can actually, see the effects that Graham's law would have even just with air rushing past our vocal cords, as crazy as that is. All right, let's go ahead and flip the page. We're going to look at a few other gas laws here. Now, these gas laws that we're going to talk about in just a moment all involve some very key variables. And so I've kind of listed out those variables that we're going to see here. We're going to see pressure. And as a reminder, some of the units that we talked about in the past that we could measure air pressure with is things like ATM, atmospheres, torr, mmHg, which is millimeters of mercury, kPa, which is kilopascals, and psi, which is pounds per square inch. Usually in chemistry, we tend to stick to atmospheres, torrs, mmHg. This is kind of the usual hangout here. If you're measuring tire pressure here in the United States, we typically do measure it in pounds per square inch, PSI, because of course we use that funky customary American system. But in science, we don't use PSI a whole lot, so we don't see that very frequently, but it technically is a measurement. For volume, we'll see things like liters, milliliters. However, we could also see things like where we have a length times width times height. So we could see things like centimeter cubed or feet cubed or meter cubed, any of those kinds of things. I'll be honest, for gases, we're typically going to see much bigger volumes. So things like liters is more common to see than milliliters. And there are some formulas where we have to be really careful about which of those volume units we use. So we'll talk about that on another day. The ones we're going to use today, it doesn't matter, but some of the other formulas it does. Now, here's a big one that really makes a difference. For temperature, remember, we need a scale that has no negative values. And so Kelvin is going to be our winner there. Now, as a reminder, the conversion between Kelvin and Celsius is super easy, and it is on your formula chart. So here's our formula chart, yay. So don't forget that Kelvin is just equals to that degrees Celsius plus 273. So you're going to see us using that conversion a whole lot, just as a warning. The other thing that's on here, I will should go ahead and show you, is those pressure conversions between our different units. So if we needed one or another, we could use our formula chart to help us set up that conversion. And we'll kind of recap how to do that here in just a little bit. Amount is our last one that we see, and surprise, surprise, being in chemistry, that amount is going to be in moles. So kind of make sure you're familiar with the different units that you're going to be using. So again, some important things as we do some of these gas laws here in a moment. Temperature must be in Kelvin. We already talked about that. It typically doesn't matter what unit pressure and volume are in, at least for the ones today, as long as you're in the same unit. So we will be kind of double checking our units to make sure they match up. And so that may mean, say for pressure, that we'll need to convert between one and another. So again, this is on your formula chart. And so we'll practice converting here just a little bit. We also want to watch out for sneaky numbers. Sometimes in these problems, there are a lot of times some sort of math problem, and we need to write down what variables we're at. And sometimes instead of giving us a number, they will just say, hey, you're at STP conditions. And so you're thinking, well, STP conditions, what's that? So don't forget, that is also on your formula chart. STP stands for standard temperature and pressure, which is 0 degrees Celsius in 1 atmosphere. Now on here, it does have 0 degrees Celsius because that's what they have on the AP formula chart. But remember, 0 degrees Celsius is the same thing as 273 Kelvin, and we would much rather use that in Kelvin than in Celsius. So you'll see us kind of, write that equality quite a bit. All right, so now let's talk about gas laws. And I went ahead and kind of filled this whole thing out, and we're going to talk about it in pieces here. I'm actually going to start at the bottom of this chart, as weird as that is. So way down here at the bottom of this chart, there's a formula on here that says combined. And I crossed off the independent, dependent, control, and math relationship variables. We don't have that for combine. And I wrote a formula on here that says P1V1 over N1T1 equals P2V2 over N2T2. This is what is called the combined gas formula. And the good news for us is that if I look on my formula chart here under behavior of gases, you will see that lovely equation on here. Yay! It's there. It's there for you to use. No big deal. However, the other gas laws that we're about to discuss are not on here individually. We're going to have to manipulate this around in order to get the variables that we want, okay? So keep that in mind. Now, I'll be honest, the combined gas law actually came after these other ones. A lot of these were done in like 16, 17, 1800s kind of time frame. And once all of these other individual ones were kind of created and proven, then eventually someone came up with the combined gas law and kind of put all of the laws together. So keep in mind that these weren't all done at the same time, that, over time, as things progressed, we were able to figure out all of these different relationships. So the first one was Boyle's law. And Boyle did experiments where he manipulated volume and pressure. Now, usually volume ends up being your independent variable. It's what we select to manipulate around. And as a result, we'll see changes in pressure. Okay. Now, if you had, say, a vacuum pump or something like that, you could flip this experiment around. But I'm going to tell you right now, Boyle did this with manipulating volumes and recording the different pressures. Okay. And typically, again, that's how that experiment would be set up. Which means if those are the variables that we're manipulating, that the other two variables would be held constant, that they would be considered our control variables. So both N and T are going to be controls here. Now, before we talk about this math relationship, I want to kind of us to visualize this law in action. So let's say I have a container that's this big, and I have some gas molecules in there hanging out, okay? And then I'm going to take that container, and I'm going to make it smaller. Think about what would happen to those molecules. They went from having all this space to hang out in to being really squished in that small amount of space. So what would happen to our number of collisions? Well, hopefully we realize if I make that container smaller, there's going to be a whole lot more colliding happening in there, right? Well, if I increase the number of collisions, what would happen to my pressure? Well, if I increase collisions, pressure would go up. So that means as I made that container smaller and squished all of those molecules together, collisions went up, and so therefore pressure went up. Now, when one thing goes down and the other thing goes up, in math we call that either an inverse or an indirect relationship, right? Now, to get our formula, this is where we're going to use our combined. We said just a minute ago that the number of moles and temperature would remain consistent for this. It would be constant, okay? So if I come down here to the combined formula and I cover up N and T, assuming those stay constant from side to side, I see the formula of P1V1 equals P2V2. Well, that's the formula that goes right up here. Okay. Our next one was Charles. He did experiments, and actually he and Gay-Lussac kind of worked together, ironically. But Charles's experiment had temperature and volume. And typically, temperature was the independent variable. You would heat something up or cool it down, and they would have a container that could expand and contract. So not a rigid container, but rather an expandable container. And so they would measure what happened to the volume of this container. And as they did so, they kept the amount of gas constant as well as the pressure constant. And what they saw is that they heated it up, and thinking on a molecular level, if we heat up those gas molecules, what happens to their movement? Well, they move a lot faster, right? And think about, if they're moving a lot faster, would they want to stick together or spread out? Well, hopefully we realize if I'm heating them up and they're moving fast, we want to spread out then at that point, right? So if we're spreading out then, what happens to our volume? Well, it would increase, right? So that means as temperature goes up, our volume would go up, and that is a direct relationship. So again, if I go to my formula down below and cover up the control variables, so N and P, if I came down here and covered up N and P on either side, I would see V1 T1 on this side and V2 over T2 on this side. There it is. Now notice here, this formula is divided versus multiplied like the first one. Well, that's because here I have a direct relationship instead of an inverse relationship. And so you can see that changes our math up when we're setting up, say, a proportion for this. Gay-Lussac's experiment used temperature and pressure. So again, usually temperature was the independent variable. They would heat things up, and this time we would use, say, a rigid container, one that couldn't expand and contract. So maybe like a container made out of metal or something, you know? And so what would happen is, again, as I heat it up, what happens to our movement of our molecules? Well, they move faster. And here's a problem. They want to spread out, but that container now is rigid. And so they can't spread out. So what would happen to our number of collisions inside? Well, hopefully we recognize that those number of collisions would increase. And so therefore we're going to see that increase in pressure. Again, we have a direct relationship. Again, if I cover up N and V on the combined formula, what would get left behind is P1 over T1 equals P2 over T2. Now, our last law is kind of a two-parter. This first part of it, Avogadro's, N and V, number of moles, and the volume are the two things that we would manipulate. And this part of the law is going to sound kind of stupid, but there's a smarter, I guess, second part to his law that we'll talk about in a second. Number of moles, that means I'm putting more gas into the container. Now, if I have temperature and pressure constant, think about it like this. If I put more gas into a balloon, if I blow more air into the balloon, what happens to the volume of the balloon? I would hope that we know that the volume's going to expand, right? Like, hello, I put more gas in there. The volume's going to get bigger, right? So this part of the law here, thinking, seriously, Avogadro, you're so smart. You came up with that, like, Avogadro's number and all this, insanely smart stuff. This is your gas law. Well, this is only part of it. We're going to talk about the other part in a minute. But you could calculate with this. And so again, you would cover up the temperature and the pressure over here, and you would end up with V1 over N1 equals V2 over N2. Now we're going to calculate with all of these in just a little bit in our second video for this. So kind of keep that in mind. You're about to do lots of math. Yay. Some of you are excited because you're like, yes, math. I'm excited. I love the math problems. Some of you are like, dang it, I don't like the math as much. But I will warn you that sometimes we're asked kind of some thinking questions about these, and I'm going to run through a couple of those with y'all here in just a few minutes. All right, so let's go on and flip to the next page. These next pages kind of give you a little bit of a summary, a background of the different laws. So again, it's the same stuff we talked about on the previous page. It just kind of gives you a little bit more, but one of the important things that these pages show are the graphs associated with these laws. A lot of, the work that was done to prove their point before they published these in journals, in scientific journals, is actually making measurements and graphing their results and obtaining the same graphs over and over again. That was how they were able to prove their points on these. The one that always throws people off is Boyle's law. Again, that's an inverse relationship, right? And so you notice the graph is kind of interesting. A lot of people want to think it's like a straight decrease, but the problem is if I had a straight decrease, that eventually if the pressure got high enough, the volume would get to zero, and that's not what happens. It's like, approaching zero, but it never quite reaches it. Same thing goes here. If that pressure gets low enough, the volume gets, infinitely higher, but it never, reaches some maximum value. So it does do a curve graph, so be very careful. And the way they figured out that this is a direct inverse, that it's a perfect inverse, is that they actually went and graphed the pressure and the inverse of volume, and they saw it go up. And so they realized that there's a direct relationship between pressure and the inverse of volume, that the inverse graph is direct. So that was how they were able to prove it was a perfect inverse there. Charles's law and Gay-Lussac's law, their graphs are going to look very, very similar. You're going to have your temperature and your volume on Charles's law. As one goes up, the other goes up. Kind of an interesting tidbit is Charles's graph as well as Gay-Lussac's graphs are the way that we figured out that absolute zero happens at negative 273 degrees Celsius. That's how they came up with that equivalence point between the scales. What they figured out is that every time they were graphing these in Celsius, that it would always trend back to negative 273. And so they figured out that that must be some absolute temperature that's the lowest we can possibly get. So kind of interesting that gas laws are the reason why we know about absolute zero. And then Gay-Lussac's is on the next page. And again, we can see that that graph looks very similar. Again, here we just have temperature and pressure involved, okay? One of the things I do want to mention really quick is that a lot of times we are asked to identify the difference between Boyle's, Charles, and Gay-Lussac's law. So I want to kind of give you a trick for that. And hold on, let me grab this back for just a second. So if you're ever trying to identify these, this is the funny little saying I use. If you don't like my saying, you can make your own. You are not going to hurt my feelings. But when I'm trying to remember Boyles, Charles, and Gay-Lussac, here's my silly little saying. I remember that Boyle is vice president. Charles watches TV. And Gay-Lussac uses toilet paper. And you're like, what? Boyle's vice president, Charles watches TV, and Gay-Lussac uses toilet paper. And you're like, those are the craziest sayings ever. But what they'll help you to do is if I have some sort of experiment and I'm trying to figure out whose law it is, it'll help you remember which one had which variables getting manipulated. And so we'll practice with that here in a little bit. But I do want to, for just a moment, talk about kind of the other quirk to Avogadro's law that makes him sound a lot smarter than he sounded just a few minutes ago. And that is that the other part to his law, besides I put more air into a balloon and the volume gets bigger, is that he said that equal volumes of gases at the same temperature and pressure would contain equal number of particles or moles, even if you have two different gases. What that means is that all of those gas law equations that we looked at can be utilized the same regardless of what gas you have, that the molar mass of it is not going to impact the temperature, volume, pressure relationships. And that's actually really helpful for us. The other really helpful thing he came up with that ties to this statement is the conversion that we've always used for gases at STP, that 22.4 liters equals 1 mole of gas at STP conditions. And again, if you think about the statement here, equal volumes of gases, 22.4, at the same temperature and pressure, STP conditions, contain equal number of moles, 1 mole of gas, even if I have a different gas. Like I can use this conversion for literally any gas. The molar mass itself doesn't matter. So very helpful. So again, I promise he was smart. Came up with more than I put gas into a balloon and the balloon gets bigger. All right, before we jump into some math, I want to talk about what I like to refer to as thinker questions, where they are gas law problems giving us some real life situations and wanting us to kind of think about, well, what's happening in these different scenarios. So the first one here says that Charles did a lot of work with hot air balloons when he was, doing all of his experimentation and stuff. He did a lot with kind of figuring out how hot air balloons work and kind of explaining why they did the things that they did. So it says a hot air balloon works by heating up the air in the balloon. If you've ever been to the Plano Balloon Festival, they have those engines on them that, blast fire into the balloon itself to heat up the air inside. And then what happens is eventually that balloon rises up and eventually it'll float away if you, don't tie it to the ground. And it says to explain why this works using gas laws. And it says, hint, think about why one substance floats on top of another. Well, hopefully we remember, like when you're dealing with liquids, that liquids stack, one floats on top of the other depending on their density, right? How tightly packed are those molecules? So let's think about this for a minute. If I have a hot air balloon where I'm like, pulling on the cord, getting, the flames to come out and all that good stuff, that would cause the temperature to increase in that air, right? Okay, well, let's think about what that would do to our molecules inside. And hopefully we know that that would make our molecules move faster, right? And as they move faster, guess what else they're going to do? Are they going to stick together or spread out? And hopefully we recognize they are going to spread out. So initially that hot air balloon, is flat on the ground until they blast that engine and then that balloon starts to expand. Now, as it expands, your volume would increase. But the other thing that happens is as those molecules are spreading out, the density of the gas in the balloon would decrease. So what basically happens is that eventually, if you untie the balloon, that the balloon will rise to a certain point where, yes, there's a density that's in here, but it's at a lighter density, a lower density, than the density down here, that this would be at a greater density. It floats to a point in the atmosphere where anything below it is more dense and anything above it is less dense. It kind of finds that perfect point. And as I, fly the balloon, if I want the balloon to land, I need to let some of that air out so that density can kind of compact itself back together and bring that balloon back down. All right, some other ones. Some of these are kind of silly, like this one's kind of silly, right? If you sit on a closed bag of potato chips, it will pop. Why and whose gas law does this demonstrate? If you have your closed sealed bag and you sit on it, it'll go boop, but let's think about why. When you're sitting on that closed bag, what would happen to our volume? Well, if you're sitting on the bag, that would cause that volume to decrease, right? But here's the problem is as I'm decreasing that volume, what's happening to the molecules inside? Well, they're getting squished together. They're colliding more with the walls of the container, and that container can only withstand so much pressure before it pops. And so let's think about whose law would this be? So this is where it's really helpful to know those silly sayings. Boyle is vice president. And so this would be Boyle's law. All right. The next one is kind of an interesting one. Next time you go on an airplane trip somewhere, okay, buy a bag of something like potato chips, pretzels, I don't know, something that has some air in the bag. Buy a bag of something at, one of the little stores before you get on the plane, or bring it from home. But leave it sealed and let the plane go up. Woohoo, leave that sealed in your bag and wait about, I would say probably a good hour into the flight. Usually like when they start serving drinks and stuff, okay? You want to get a good height on it. And if you pull that bag back out, what you will see is that it's like expanded and blown up basically like crazy, almost to the point where sometimes it's hard to like get open because it's so, increased in that volume. It looks like it's about to burst, okay? By the way, the same thing happens with the gases in your intestines, which is why you wear stretchy pants on the plane. Okay, so let's think about what's happening. What happens is that even though that airplane cabin is pressurized, it's still a lower pressure than at sea level. Like the air pressure in the airplane is not as great as it is when you're down on the ground. I mean, it's not as low as it is outside of the plane, but it's still pretty low in comparison. So that pressure has decreased on the outside of the bag. And, here I put of bag. Okay. So let's think then, what would that do to the volume of what's happening in the bag? Well, if I'm not pressing as much on the outside of the bag, the molecules that are inside are like, ooh, I don't feel as much pressure. Let me start to spread out. So that will cause our volume to increase inside the bag. And that's what causes that bag to blow up. I mentioned a minute ago, this is why you wear stretchy pants, right? Because all of the gases like in your intestines and your stomach and stuff expand and contract as you're going up and down out of the air. Same thing with the pressure in your ears. When you rise up, that pressure gets so much lower. And like if that pop hasn't happened yet, that pressure builds up inside of there. And then all of a sudden you pop your jaw or something and your ears feel like they're, going to burst on you because all of those pressure and volume changes are occurring. Who's gas law? Well, again, think about who's vice president. That would be Boyle, right? All right. We got two more here. Tires on a vehicle need a certain level of pressure in order to run optimally. Why are people encouraged to check their pressure of the tires in both the summer and the winter? Whose gas law does this demonstrate? So let's kind of think about, first off, summertime. I know we're all very excited about summertime coming, right? Well, what do we know about summer, especially here in Texas? Well, our temperature shoots up through the roof, right? Okay, well, if the temperature shoots up, now, I will mention this about tires. I know tires can go flat, but at some point, the tire is a fairly rigid container. Like there's only so much that tire can expand at some point before it goes rigid and you're kind of stuck there, okay? So let's kind of assume that volume is not going to be changing all that much, okay? What will be changing though is pressure. And let's think about how. if my temperature is going up, what is that going to do to our molecules? Well, our molecules are going to be moving faster. They're going to be wanting to spread out. But again, that tire's kind of rigid, so it can't really spread out any more than it is. Well, what's that going to do to our number of collisions? Well, our number of collisions are going to increase, right? And if collisions increases, what happens? Oh, that's right. Pressure goes up, right? And so what happens is that in order to decrease that pressure, sometimes you have to let a little air out of your tires. That pressure can get too high during the summer in your tires. In the winter, the opposite happens. Of course, in the winter, the temperature goes down, right? And so the pressure goes down. I know on my car, first time the temperature really decreases, very cold outside, like the first, real good cold snap that we have. What happens is that my car will ding at me like, oh, the pressure's low in your tires. And you go to like one of the gas stations that has where you can fill up your tires with air. And it's like a long line of people all waiting because all of their cars dinged at them too, because that pressure's gotten too low. And so we've got to put some more air back into it in order to get that pressure increased again. If your tire pressure gets too off from its optimal value, that can cause issues on the wear of your tires. It can also make your tires more prone to blowouts. And so that's why you got to really maintain a good pressure on your tires. And you got to be conscious of what that value is. All right, so let's think about whose gas law this is, right? TP, who uses toilet paper? Oh, that's Gay-Lussac, right? Yeah, all right, last one down here. All right, last one, and it's a trick. We got to be careful. It says, hey, if a gas changes its temperature from 100 degrees Celsius to 200 degrees Celsius, does this mean that the volume has also doubled if the pressure is constant? All right, so here's the deal. It's talking about temperature increasing and what would happen to our volume. And it's asking, would it double? Well, we know as temperature increases, that means our molecules are moving faster, they're spreading out, so we would expect the volume to increase. And they should do so proportionally. But don't forget something really important about those proportions, especially with regards to temperature. Those proportions are only true in a temperature scale that has no negative values. Well, notice what we've got here. We have Celsius. So let's convert these Celsius temperatures into Kelvin by adding our 273. So 100 degrees Celsius would be 373 Kelvin. 200 degrees Celsius would be 473 Kelvin. So look, did those double in Kelvin? Nope, they did not. So we have to be really careful about saying we double temperature in Celsius. You didn't really double kinetic energy. If you had doubled it in Kelvin, you would have. But doubling in Celsius is not the same as doubling in Kelvin. So the answer to this is no, only because our temperature did not double in Kelvin. If it had doubled in Kelvin, would your volume had doubled? Absolutely. But because it didn't double in Kelvin, it did not double that volume. Last but not least, whose gas law does this demonstrate? Well, who watches TV? Oh, that's our good friend Charles, right? All right. Sorry this video ended up longer than I was anticipating. Hopefully you're feeling really good about having a nice foundation with all of these various gas laws. In our next video, we're going to look at calculating with all of these gas laws. So we'll be manipulating all of our equations around to see if we can solve for an unknown variable. If you have any questions or need any help, please feel free to email me. Bye, guys.